Welcome everyone. Thank you for coming out for the last Talk About the Business seminar series for this semester. For those who don't know me, I am Jean-Gabriel Young. I'm an assistant professor at UVM in the Mathematics and Statistics department. I also work with the Complex Systems Center. And so as a reminder, I was saying the talk today is going to be recorded, so behave according to your privacy preferences with this knowledge. We'll put it up online to access at the UVM Complexity, where all our season is uploaded, so you can look back at our talks. Also, as a reminder of the norms, we aim to be a playfully serious and inclusive space. So in the way you kind of interact with the speakers, keep these norms in mind. And so with these words, it's my pleasure to introduce Benjamin Golub today. He's a recently professor of economics at Northwestern. I think got promoted a few weeks ago, so congratulations, Benjamin. He got his PhD from Stanford in economics, working with Matthew Jackson, who, as many of you know, wrote literally the book on social and economics networks. He has since gone on to be an influential researcher of his own, first as a fellow at MIT and Harvard, then a professor there, an assistant professor there before moving to Northwestern. His work has been recognized with many prizes, including the Career Award, as well as the Calvo Armengol Prize, which is given to kind of young economists under 40 for their contribution on social influences. And when he's not found tweeting about eigenvector centrality, he's researching game theory on networks, financial contagion, and learning on networks. So welcome, Ben.
Thank you so much for that super generous introduction. It's really an honor. I am delighted to get to speak to this group. As I was saying just before we started, it's I really feel a deep affinity, maybe more than with economists, when I talk to people who are interested in network science and complex systems. And so I've tried hard to sort of give a talk, prepare a talk that was going to really draw the connections that I see in the complementarities between economics and I think what is in the intersection of all our interests. So let me just jump in so I can try to maximize content. I'll give an overview talk on economic networks, robustness, and interventions. And the idea is really to present two different projects which are at, in a sense, opposite ends of a spectrum of what you can do with network theory and complex systems theory in economics. And so I'll emphasize, I'll take for granted more than I usually do a familiarity with network ideas and correspondingly unpack some of the economics a little more. But given that we have less common knowledge about what we share than usual, I would be super grateful if people ask me things that they, things that I can clarify. And then of course we'll have a longer Q&A after. So the first project I'll present is about supply network formation and fragility. And this is with Matt Elliott at Cambridge and Matt Leduc. These are both economists, and Matt Leduc is at the Paris School of Economics. So let me just jump in and say what we're about. We're interested in complex production, which is a process where there are many steps, each putting together several essential inputs. And this is basically all modern industrial production, but let me give you just a very toy example to make things concrete. Imagine you have a little airplane manufacturer here, and the airplane manufacturer has, just for the sake of the example, sourced everything they need to make the airplane except for two inputs called brakes and computers. And in order to source these brakes and computers, the firm relies on specific relationships, specific contracts with particular suppliers. So it can't just go to Home Depot and say, hey, give me some airplane brakes. That's not a possibility. It has to rely on this particular contract that's established with brake manufacturers that the regulator has cleared and so forth. And this brake manufacturer is in a similar situation in the sense that it sources certain inputs, let's call them disks and computers. And these are also from specific suppliers that it has contracts with. Dotted lines means there's a possibility of placing an order to that person to get that, to that firm to get that input. So think of these as little firms in the economy. Little in the sense that they're not going to be like in themselves systemically important. They're each small in terms of their total output, interacting with each other. Now, the implicit assumption I've been discussing that firms are really reliant on specific suppliers has recently been explored extensively. I mean, there's a lot of antecedents for it actually in network science, papers I haven't mentioned, but kind of gold standard empirical evidence has recently been obtained in several different economics papers. It seems that firms really are reliant on specific suppliers. They can't just substitute easily if their links fail. And that makes us interested in the specific functionality or not of particular sourcing relationships. And so firms not, a core tenet of economics is that firms are not stupid. And so they, in view of the disruption risk they face from this stuff, they're going to respond by investing in a deliberate way in these relationships. And so they're going to be multi-sourcing, maintaining multiple sourcing possibilities, and investing to make them operate enough. I mean, in a sense, I have many relationships, and the idea is that if I invest enough, I can achieve a pretty good chance of having what I need for each type of input. And the question, nevertheless, despite firms optimizing and being careful about this, we want to understand the robustness of the aggregate system. So a very classic network kind of question: how robust is the network going to be to shocks that reduce the probability of links working? Now, I want to be very clear about two different shocks you can think of. There's idiosyncratic disruption, which is what can happen to a particular firm. So my particular relationship with this supplier doesn't work because the ship didn't arrive on time, because there's shipping disruptions, and the congested ports mean that my shipment is delayed and I don't get my inputs this period. And then there's aggregate shocks, which are not just the realization of that for every link, but the changing the probability for everyone that links work, which is like the ports getting more congested. So we'll have both of these in our model, and we'll be interested in the impact of aggregate shocks. And our main question will be, first, what's the physics of this system? How robust is it to shocks in the probability of each of these relationships working as desired? But second, when, as I told you, firms are deliberately investing to foster these relationships, will investment in robustness result in robust or efficient, or in some sense good outcomes, or are there deep kind of problems in the system despite firms' optimal behavior? And the main finding of this paper is going to be that there's what I call a fragile regime, where aggregate output, that is how much this economy or this production network, which is very large and contains many, many, many little trees like this, when will such a large network be very sensitive to small systemic shocks, to these relationship strengths? And what we'll see is that it exhibits a kind of discontinuous phase transition, where many supply chains suddenly and inefficiently freeze. And this is not just a possibility in the physics, but it's something that's naturally going to be favored by the optimization forces operating within the system. So this is a kind of self-organizing criticality coming about in a macroeconomic model of firms investing in network robustness. And in that, it's new in the sense that, the self-organizing criticality is obviously a core idea in network science, but bringing it to a full-fledged bells and whistles economic model that has firms doing all the things that we like to think of firms as doing, that hadn't been done. And we're very excited that there's now emerging, there's sort of now a new link between these ideas. And this paper, I didn't put it on the slide, but it was published in August in the American Economic Review. So in terms of bringing this to a real application, a pretty good application to fix ideas, at least, is the COVID shock to the world supply network. So when COVID hit, people started spending a lot less of their money at restaurants and a lot more of their money on physical goods produced by industrial production. And the fact that the world shipping network was shipping many more TVs and treadmills and so forth resulted in shipping network stress that affected most supply networks, even those not directly affected by any kind of COVID shock, or those that recovered quickly from direct COVID impacts, still had to contend with the fact that the world shipping network was just clogged up. And so the shipping network was putting through more goods than it ever had before. So it wasn't failing, but the fact that it was so congested meant that the typical thing you were shipping was going to be subject to delays that were unusual. And that incorporating that into a model of macroeconomic production with this multi-tier sourcing hasn't really been done in the economics literature. The closest is a literature that's emerging, and I just want to mention it for those of you who want to dig deeper. We cite a lot of papers in this macro literature. Bakai and Farhi are perhaps the most important in this, the closest to us and the most important antecedent for us. But macroeconomists love a smooth model. Ultimately, they'll write down a model of all this complex production, but their goal will be to get an aggregate production function, the outcome that you care about, which depends maybe on the shipping links and everything, but it'll ultimately be a nice smooth function that they can differentiate to do their standard macroeconomic analyses. And as you know from network science, we are interested often in cases where the aggregate behavior of the system has fundamental discontinuities, fundamental non-smoothnesses, and bringing that to the economic models is sort of what our focus is. So, and as I said, there's evidence, that these are real things at the firm level. We're interested in the aggregate level. So I'm going to dig just a little deeper into the model, and this will really give you a sense of what we do mathematically. So small firms have supply relationships to other small firms. A typical firm needs to procure several inputs to produce, and it's going to have multiple potential sources of each input, where each of the links delivers what you need. And this is new relative to the slide you've already seen. This is the part of the model where the stochastic outcomes are happening. Each of these links is going to work with a certain probability X independently of the other links. So X is kind of the key parameter in this model. And the key idea is that, so this airplane manufacturer has each of its links working with probability X. And these suppliers of it are in the same position, but one step less deep, but they're also reliant on these these links that are subject to random disruptions. And then once we get to the most upstream layer, maybe not this one, but at some point in the network, some firms don't need to rely on any disruptible sourcing. They can just buy their inputs off the shelf or in some other way that's not going, we cut off the model there, and those guys are going to be reliable for sure without any of this disruption risk. So let me just show you in an example how that actually looks and the key physical outcome that is going to be at the center of our analysis. To a physicist, I would say that the outcome that for now, for this little tree, the outcome I want to study is just the reliability of production of a particular firm. Let's focus on A1, this little airplane firm. So all I want to ask is, what is the probability that firm A1 can actually produce its good? And I call that the reliability of this firm. So of course, it's going to depend on X, which is the disruption risk to each link, or the non-disruption. So X is strength, bigger is better. X is relationship strength. And D is the depth of production, which in this case is 2 steps high, 2 steps deep, right? And I should say in terms of my pictures, higher is upstream. So orders go upstream and products flow downstream from more primitive to more more put together items. Okay. So what I'm interested in is Mr. A1, can you produce, right? So how will I find that out? Well, I'll show you in an example. So the first thing I'll do is I'm going to percolate this network, which means I keep the links with probability X, and the grayed out ones, the ones that disappeared or got grayed out, those got killed with probability 1 minus X. This was independently at random. And so now I'm going to figure out whether A1 can produce starting from the top, working backwards, if you will. And so I'm going to say, well, let's look at B2. Okay, B2 has some inputs here, the G input. And as you can see, neither link to the G input is working. So that means that for whatever time period we're interested in, this G input just didn't get there in time. So we can't, we don't have it. So B2 is going to turn red, meaning it can't work just because in this time period, it can't get that input. And now if we look at our airplane manufacturer here, it does have the shipping link to B2 would have worked. That ship would have arrived on time, but unfortunately there are no brakes to ship. So that's not going to work. And the other brake manufacturer who happens to be operating, that shipping link does not work. And so as a result, A1 is also not operating. So for this particular percolation realization, there's no way for A1 to get one of its essential inputs, the brakes, and therefore A1 is not operating in this time period. Now, as you can see in this example, reliability depended on the depth. I only had to do 2 steps of this reasoning. You could turn this into probabilistic reasoning, averaging over all these outcomes, but of course it would depend on the depth. And so what we will ultimately not just be interested in one tree, but a whole collection of such trees producing all these different things together. So we'll be averaging over these reliabilities across different depths. And we'll be interested in how reliability responds to shocks, especially moderate or small shocks that affect everybody's probability of relationship functioning. So each link is going to work somewhat less well, and we're going to be interested in what that does to the aggregate productivity of the system. Maybe this is a good time to stop and ask for clarifying questions on anything I've said.
We have one here from Mariah.
Hi, I'm just curious if you have thought about changing the percolation probability at each layer, unless you, again, it'd be much simpler to just assume that each like B1, B2, or A1 have the same percolation probability for those failures within this entire, say, like type of industry system. But given that they're different parts, you could assume that there's some heterogeneity in the failure systems.
Yeah,
possibly.
that's a great question. Thank you very much. Yeah, so this provides a great opportunity to say that what I'm going to show you in this talk is a very Mickey Mouse ultra-symmetric model with whose symmetry is justified only by me really wanting to draw some one-dimensional pictures for you, which is obviously going to be a lot easier if there's only a kind of a one-dimensional richness to the system. But a lot of people suspected that the stark phenomena I'm going to tell you about would actually not even be there if you allowed for the kind of heterogeneity you have in mind, or perhaps other kinds of heterogeneity, like different numbers of sourcing inputs. You know, if you disrupted the homogeneity of this tree in various ways, you might think that the physics of it and also the economics would really change. So we have an appendix in which we work out heterogeneous models, and we have thought about that. But I want to sort of say that, like, I believe the forces I'm telling you are pretty robust, and yet the symmetry that you just criticized is key to getting across, you know, the first pass. But that's an awesome question, an important robustness test of the whole theory. Okay, so I'm going to go quick, but I do want to give you some sense of how economists like, and actually this is maybe the biggest model I've ever worked with. It made me sort of really respect how much macroeconomists have to keep track of if they want to have even a mildly rich model of, let's say, industrial production. So I'm going to tell you at a high level, but still with some detail, what kind of economic model we build around this core idea that I've sketched. So we have the key model ingredients are going to be a finite set of products, which are airplanes, brakes, computers, and so forth. Now, in each of these products, we're going to have a continuum, like an interval. You can think of an interval of real numbers, the interval, say, 0 to 1 or whatever, of real numbers, of firms indexed by real numbers that specialize in producing that kind of thing. But the varieties are differentiated, as economists say, which means that different kinds of little airplanes that are made, like the Cessna, the Piper, the Cirrus, are all different things that different people prefer. And it's more valuable when more of them are available because people like different styles of this thing. In terms of notation, when I write 8.1, I mean the airplane industry firm labeled 0.1, okay? Now for each of these types of goods, like airplanes, we're going to specify a set of essential inputs, which is what's needed, what's indispensable for producing that thing. So we saw with, you know, in this little example, it was airplanes need brakes and computers. They actually need 1,000 things. So you would have a bigger set. And now critically, each of these varieties has a certain depth, which means the number of steps of specialized sourcing in the tree needed to produce that thing. And so I'll specify that for every variety, you know, so the depth of a particular firm, like 8.1 might be 2, as in our example. But actually in the whole economy, what I'll be interested in is the distribution of depths, because I'll be averaging over the whole economy. So maybe there's maybe 17% of the goods have a depth of 10. And that's the kind of information that's captured in this distribution mu. And if you want to think of a concrete example, and in fact, you know, our main results will be taking this distribution and taking it in some sense to infinity, making depths big, at least to make the key conceptual point. So if you want a concrete example, think of it as a Poisson distribution with a certain mean that you get to control as the modeler, okay? And so that's kind of what there is. And once we have that, once we have those primitives, once we have that notation, we can construct a graph on a continuum of nodes. So it's sort of a big, it's a a somewhat amusing object, if you like to think about these things. It's a graph on the set of all firms. So you take the union of all these little airplane firms and brake firms and so forth. And I'm going to specify a random graph on this big set of firms by saying that, let's, and to the question that was asked, I'm going to impose a lot of symmetry on it. But the idea is basically for every firm, if it's positive depth, which means it needs inputs, it's going to need m distinct types of inputs, m distinct input categories. And for each of those input types, like brakes and computers, it's going to draw some fixed number, n, of potential suppliers for that input in some atomless way. Let's say according to a density, it sort of grabs suppliers and says, okay, I'll have 3 suppliers. And the key thing is that both the number of inputs you need, the complexity of production, and the number of sourcing options you have for each thing is held constant. So these 2 numbers are held constant throughout the economy. And again, this you would want to make a much richer heterogeneous model, which we can do. But for this, we're going to fix those parameters. And of course, if you're a depth 0 firm, you need no specific sourcing. You're just going to be able to produce for sure by assumption. And so that's going to give us a big random. I mean, you could realize this in your computer for, just with the large number of firms. So you somehow cook up this big random graph. And then you say, okay, well, actually, my operational links are going to be a subset of these potential links. I'm just going to keep links independently with probability X. Those are going to be the sourcing possibilities that actually work. Okay, so that's sort of the big economic graph. We're going to be once we have this graph, economics is going to happen on it, and I'm going to spare you that. So you go to you take a semester class in general equilibrium macroeconomic models, and you figure out how to, once you have this production, think of it as a substrate. This is like what production can happen on. Then you actually need to do the production. Yes, so somehow or other you do it. And at the end of the day, when you do all that work, what you get is that this is what matters. Okay, what matters is the share of functioning firms. So remember, we talked about the reliability of one firm, which is just the probability that A1 could function. Now we're going to average over all various depths in the system, and get a reliability function that depends on the depth distribution, and of course also on X, which is the reliability of links. And the reason that I say this is what matters is that when I do the economics behind the curtain, the equilibrium welfare, the outcome that economists care about, is a smooth increasing function of this rho. So if you'd like, you can think of this as a welfare index. The higher this is, the more happiness juice the economy produces. We have more different kinds of airplanes, the economy is richer, okay? More varieties functioning ultimately makes for a happier consumer. And what we're interested in is how this reliability looks as a function, for now, just the physics of it, how it looks as a function of X. So now I can show you my first result, which is this picture. So in this graph, I varied on the x-axis relationship strength, and on the y-axis, I'm plotting the reliability for a particular depth distribution. I think I chose Poisson depth 10 here, okay? Average depth 10. So you can see that there's a somewhat stark behavior here, where for low relationship strengths, the number of varieties that can function is very small, and then above some cutoff, suddenly the number of varieties functioning is quite large, right? And there's a very stark transition. And then as I make the average depth deeper and deeper, so I look at any distribution where the probability on depths that are small, which is to say, probably once the average depth runs off to infinity in the Poisson case, this picture becomes this picture. So you see a super stark transition, where up until a certain value of X crit, a certain strength level called X crit, you can't do anything. No varieties work. Then you cross X crit, and suddenly like 60% of varieties work, right? So this is what we call a precipice. When supply networks are deep, meaning that average depth is high or typical depth is high, and they're complex, meaning that you need and I'll explain that caveat later. There are precipices where a systemic shock, even a small one, can bump you off of being able to produce a lot to being able to produce very little. Mathematically, so complexity means M. What was M? It was the number of different things you needed to source. When everybody needs to source at least 2 types of things, then you have this phenomenon where there's a positive X crit, so that for below that, you can't do in the limit anything, and above that you produce above some strictly positive level R crit, right? And I want to contrast this with a different picture that you would get if you had m equals 1, which is what I call the assembly line, where at every stage of production, you only need to source one thing. So think of an assembly line where you pass along the assembly and you add just brakes here. So you may still have multiple options for sourcing brakes, but you only need to add one thing at that stage. That's an m equals 1 process. And there, this picture would look very different. You wouldn't have a precipice. And in fact, the math of this is exactly the same as the math of the standard viral or branching process. It's a standard branching process, which has this kink, but no discontinuity. But when you put in the complexity, 2 things at each stage, you get a complex contagion picture. I don't know if you guys know a famous Watts and Dodds paper that observed this. So complex contagion begets these discontinuities, and you see this in a kind of economic context here. And so, yeah, so that's sort of the finding. I wish in a longer talk and maybe in the Q&A I could show you where this is coming from, but let me pause again and ask if there are any questions about what it is I'm saying.
I have a question.
Yes, we have questions here.
So when you're saying share of reliable firms, does that share of like all firms, including those of depth 0, or like is it just all production, like just the airplanes and not the computers inside?
That's a great question. So when quite loosely here, I'm saying that as the depth distribution goes to infinity, what does that mean? It means for any segment 0 to k, where k is any number, the probability, the fraction of depth of firms of that depth is going to go to 0. What does that mean? That means that the raw materials guys, a lot of people are going to be sourcing from them, but they're going to be a negligible share of the economy. If you'd like, you can call this value-weighted share of the economy. So you're absolutely right. This thing will apply only to deep firms. If you had deep and shallow ones, then this picture wouldn't hold for the shallow ones, but it would hold for the deep ones, right? And here I'm just assuming that the fraction of deep ones is going to of shallow ones is going to 0, which is not essential, but does make this picture neat. Does that answer your question?
Yes, in the limit it does, but what I'm asking is like, why do we care about anything except the final production stage?
Oh, well, that's a good question. I mean, some countries basically only. Okay, very good. In the economic model, for simplicity, we set it up so that all of these goods are valuable. All of these goods are eaten. Even the breaks are enjoyed by the consumer as a consumption good. That's obviously a silly piece of symmetry that I'm imposing. In general, though, many things like coconuts are both raw materials and inputs, raw materials for industrial production, but also just directly consumed. And so in a general economic model, you would generally care about both. But you're right that the stuff we have to say is just in some sense about the deep industrial outputs. And those are the ones that these pictures apply to. And Nicholas asks in the chat, what about loops? So very, very important. We do not, just by virtue of the way we're constructing this random network on the firms, cycles will not occur, or at least, cycles will not be a positive probability occurrence, but cycles at the industry level, where law firms rely on the transportation industry, which relies on law firms, that's possible in the network on products. But we won't have cycles among firms. And then another question in the chat, how do we get the output elasticities, set the output elasticity? So we just use some uniform elasticity throughout the economy. Obviously in the network macro literature, people have very sophisticated ways of doing this. I do want to say that, we're in a sense orthogonal to those choices will affect exactly the value of the production, but as long as your production depends in some increasing way on reliability, these kinds of forces about who can even function at all will be relevant. But we leave the setting of elasticities to the experts because we're really trying to highlight a network theoretic force. So I'm mindful of time. I have an hour, and so here's what I want to say. And I'm going to abbreviate the remainder of the talk, but the core substance of the paper is going from physics to economics. And so relationship strength, which for now I've taken to be an exogenous parameter, is of course not just given to us by some natural force. It depends on physical constraints. It depends on things like the quality of the roads, physical infrastructure, but also institutions like how well the government maintains the roads, and firm decisions like how much the firm invests in the logistics department, how good its managers and lawyers are, and so forth. And those are choices. The precipice result shows that there are parameter values where production is very sensitive to aggregate shocks. But if you're an economist, you may ask, would that outcome ever actually be a danger under standard models of optimizing behavior? And the short summary of what the kind of answers we can give to that is no. If the decision maker is a central planner, that just won't be something a planner would ever choose to do. But it will be a real live possibility in decentralized equilibrium. If the decision makers are firms concerned about their own robustness, even though they invest optimally, there's a pervasive kind of underinvestment force in this economy where they won't invest enough and they can actually put the economy on the precipice. So I could spend the last half hour fleshing out that point. I'm not going to. What I will show you an extremely abbreviated picture. So very, very roughly, we set up an economic model where firms, rather than an X being set globally, firms decide their own XIF before the supply network is realized. And that's going to determine the probability that the firm can successfully source its inputs. Of course, that is not free. If you want to source your input with very high probability, you have to pay a lot for really good lawyers and really good logistics consultants. And so we set up an economic model of that where firms do that, make those investments, and then earn profits conditional on being able to produce. And we encode into the profit function the idea that when you are scarcer, when you're one of fewer varieties producing, your profits are higher. So you have a natural incentive to want to be robust when others aren't. Now we look at our picture that I've already shown you, and we say, well, look, could you ever be at this R-crit point in a communist centrally planned economy? No, under this economic structure, you would never be there, because the improvement, if you just marginally improve X here, if the central planner decrees that everybody should invest in their relationships a little more, the derivative of reliability will be infinite there. You will get a lot of reliability for a little investment, but the marginal costs of that are by assumption just some finite marginal cost. So it would be stupid not to invest your way out of this precipice location. But it turns out that when relationship strengths are chosen in equilibrium, we can in fact put them in equilibrium right on this precipice. So think of a large but finite average depth, then this will be a very steep version of this figure. And it turns out, miraculously, the equilibrium can really like to perch somewhere around here. So that's our main economic result, that the equilibrium ends up perched in an area where the social planner would never put it, a little more formally. So, okay, what do we do in the math? We end up intersecting this physics curve, the rho curve, with some kind of best response curve that governs the economics of how people want to invest. I can talk more about that in the Q&A if people are interested. But the result we get for all of this is that when supply networks are sufficiently deep, there's going to be a positive interval of productivity parameters, which is basically how valuable output is, where at optimal investment, the firms will end up at an equilibrium. The only good equilibrium will be not up here, not in the safe space, but right here in the place where X is right on the precipice, and little shocks to X will make this production network stop working. So there's a sort of that's really what's interesting to economists, because we're not just interested in, this fragility can happen a priori. We're interested in, will this fragility happen when firms, despite kind of rational behavior? And I can talk about the economics of what drives that. I just wanted, I'll leave this maybe as a teaser. And someone asked in the chat, where is the paper? That's a great question. So if you just go on my website, there's the ungated, it's called Supply Network Formation and Fragility. And on my website, you can get the ungated version as published. So let me stop there for this. I'll come back to this and I want to be ambitious and give you a taste of something completely different. Is that okay, Jean-Gabriel?
Yes, fantastic. Let's go ahead with this plan.
Okay, so I'll unshare and I'll share something different. And I really know the question asking where my paper is the best possible question one could hope for. Okay, so let me remind you of my goal. I kind of want to spread the gospel that it's a great time for economists and network scientists to expand our friendship. And I think economists are now ready to hear some of the core ideas that network science can bring. And so here's a totally different instance of that. This is about pass-through and market power. And let me sort of link let me bring together this my slides are showing, right? Is that can you see them?
Yes.
Perfect. Okay. So this is about pass-through and market power, a principal component approach. And the previous paper focused on the phase transitions of a large network, and the main economic choice was investment in relationships. And the main methodological point, which is a core tenet, the methodological point is we can connect these important economic issues to a very central issue in network theory, which is percolation and phase transitions. But of course, once firms are able to produce, they also price and compete. So firms are not just and this is a little related to some of the questions that were asked. Once firms can function, there are a lot of interesting questions about how exactly they produce and how they price. And in complicated economies, it's hard to say anything very simple and general about that. But it turns out that there are cool network theory ideas we can apply to better understand how their pricing interacts and how the strategic forces in the system ripple through. And so this paper is about an economic application of a totally different point, a totally different tool in our network theory toolkit, principal component and centrality theory, and my favorite thing in the world, eigenvectors, and how that can inform a study of optimal intervention. So how would you optimally, as a planner, come in and help a system? And a very standard kind of economic intervention is taxes and subsidies. So this is a talk about that. Now, incidentally, in the previous paper, you could also think about optimal interventions in view of the problems that I identified. And I'm super happy to talk about that. This is different, but a lot of economic models build up to an intervention theory. And here, that's really the centerpiece. Okay, so what is it that we're doing? I'm just going to tell you what we're doing. We have a simple model of differentiated oligopoly. So there are n firms. The people in this economy are n firms and a single representative consumer or household. And I'll explain what they all do. It's a model of firm pricing. So what the firms really are doing in this model is setting prices. Each firm has a proprietary good. Let's say it has a patent and only it can sell that good. And at the beginning of the game, all the firms simultaneously announce prices. This is what I'm willing to sell my thing for. That gives rise to a vector of prices. The household sees this vector of prices and chooses quantities of each good to buy. In order to do what? In order to maximize a certain utility function of eating those goods. So the consumer has a consumer utility function, which is some concave function of the goods. That's all I'm going to say for now. And then subtracting off the prices, the money paid for those goods. So that's just prices dot quantities, right? All the goods that it bought, it had to pay for them. And the consumer is going to look at all the prices and choose an optimal bundle for itself to maximize this thing. And the firms are then going to receive profits. So the profit of a firm is the quantity that it sold when the consumer decided how much to buy, times the unit profit, which is a price, that's what it set, minus a marginal cost, which we're going to take to be an exogenous parameter of this model. So what's given to us as modelers is, the consumer's preferences, V is given, and also the costs are given. And everything else is determined by them through optimization. So a very basic fact that I have to tell you is that the products here, in general, what the purpose of this V function is it's going to link the products. So our products might be substitutes. You and I might sell slightly different variants of airplane, and then we're going to be substitutes for each other. Or maybe I sell GPSs and you sell airplanes, and then our things are more valuable together. And so then they're going to be complements, right? And so they're going to be strategic spillovers where my pricing decisions affect how the consumer values your product. And in general, in these, a core fact about these kind of models is that equilibria are not going to be efficient. It's an Econ 101 exercise to show that basically firms don't produce enough when they optimally set prices in this kind of market. And recently, those inefficiencies have become quite interesting to a very active literature in applied economics, in macroeconomics, in industrial organization. People are taking these market power distortions seriously. Even your neighbor Elizabeth Warren takes them seriously and talks about them a lot. So what we're going to do in this paper is a very humble microeconomic exercise of trying to better understand these distortions and the inefficiencies and how to fix them in this complex interlinked system by doing a very physicsy exercise, which is like, here the basic exogenous parameters are costs. So that's what I'm going to vary. The firm's costs are given and they're going to be changing due to, for example, commodity prices, wars, and so forth affect how much inputs cost. And we're going to be given a certain function. So think of C as just a dummy parameter, which I'm going to use to vary the costs. So I'm given some function C of psi. And for any other thing in the model, like prices, quantities, any other outcome, I'm going to write X dot to denote the change in that thing as I vary psi. So I'm given an exogenous impulse, and then I'm going to look at the derivatives of everything as that impulse kind of affects the equilibrium of the system. And what we're going to be interested in particular is how much a given change in costs affects equilibrium prices and consumers' welfare. So think about your local bagel place has its bagel price goes up by 10 cents. It has to pay 10 cents more for each bagel. How much of that is it going to pass on to you in the price? Is your bagel going to get 5 cents more expensive, 10 cents more expensive, maybe more? That's price pass-through. And there's a similar notion of pass-through to the economic welfare that consumers ultimately enjoy. So what we're going to offer is sort of the slogan here is that eigenvectors illuminate everything. We're going to be able to see, by thinking about this system through the lens of eigenvectors, we're going to be able to understand better which cost shocks matter for price and welfare volatility, and how ultimately should a planner think about designing taxes to best improve welfare. So obviously, I'm also going to only be able to give you a taste of this, but I want to kind of tell you that it seems to me this is a very rich interplay between a core networks idea and an economic model. So I'm going to try to sell that. So a little more formally, I'm going to fix an interior pure strategy Nash equilibrium. So a situation where all of these firms are optimally pricing against each other. Look at an equilibrium, and then each firm, has a nice differentiable pricing problem. It's going to set an optimal price, taking others' prices as given. And if you write down the first order condition, just the optimizing condition for each firm, you get this formula. This is the subscripts here are just they're not derivatives. This is firmized quantity plus a certain derivative, blah, 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 equals 0, okay? For this talk, I'm going to make a drastic simplifying assumption and assume that the demand function, the consumer's optimal choice of bundle, is actually a linear function in a neighborhood of equilibrium. So doesn't have any second derivatives. That's an assumption that we can dispense with, but stuff is already interesting even under linearity. And that's going to let us keep track of just one important matrix, which is a kind of Jacobian. Okay, this D matrix is the derivative of the consumer's quantity demanded of the ith good as the jth price changes. So I change the jth price, the consumer reoptimizes whatever she does, and it's going to change the quantity purchased of good I. So this D matrix keeps track of that. It turns out that I can normalize and assume that by just basically choosing how I measure the quantity of each good, I can make it so that the diagonal of this matrix is -1, because I can measure how much I sell of my gasoline in ounces or liters or whatever. I can choose that to make the derivatives in own good -1. And then making that simplification, we can write a very simple summary of the comparative statics of the system. So I'm basically just taking these optimal pricing conditions, differentiating them in my perturbation, in my dot, right? And I get this formula that the price dot, the change in the price vector, looks like a very simple matrix times C dot, which is the exogenously given nature-driven changes in costs. And so that's the core physics. That's sort of the given physics of the model that people have basically written down, not exactly in the same notation, but what we're going to be about is illuminating this through network theory, showing that you can actually learn something new about these comparative statics by looking at this in a particular basis. Okay, so this is what sort of the basic economic analysis of this is, and then what else can we learn about the impulse response of this system? So let me try to show you. So let me give you a tiny, like a a whirlwind review of, for those of you who haven't recently seen it, of Econ 101 on pass-through. If you have a single firm, so you can consider the one firm version of this model, when its cost changes, it turns out that price changes by half that. So the pass-through of a monopolist just selling one good is a half. If your bagel place experiences a 10% increase in cost, your bagel gets 5% more expensive, and in some sense, the other 5 cents comes out of its profit. That's how it works in the basic monopoly case. In a competitive market where you have two firms that face the same input costs and are both selling the same bagel, if their bagel, if the cost goes up by 10%, they sell the bagel at marginal cost, which is cheaper, but then you get a pass-through of 1. So the full cost increase passes through to you. So these are typical pass-throughs in super simple examples, monopolist and competitive market. In this general multi-firm oligopoly, pass-through isn't even a number, it's a matrix, because there's these end costs and these end prices, and there's an effect from each cost on each price, right? But it turns out, and my network theory friends here will be, will find this a native kind of thing to do. It turns out we can look at this system in a good basis that will make it pretty legible to us. And here we use a bit of economic magic. So it turns out that this assumption I made, a standard and often criticized economic assumption, that there's one representative household in the economy, it does have one technical payoff here, which is that it makes this D matrix symmetric. Okay, that's a magic fact. And when you have a symmetric matrix, it's orthogonally diagonalizable. You can find a basis for the space of all goods. So let's say you have 18 goods in your economy, you can find a basis for the vector space R18, where the basis vectors are each eigenvectors of your D matrix. That's what it means to be orthogonally diagonalizable. And in this basis, D will be diagonal. The virtue of that approach is that rather than talking about outcomes in the original units, so before I told you this, you could have said, okay, let's describe outcomes as 15 units of Elizabeth's good and 2 units of Hernando's good and 1 unit of Ben's good. Now you can just re-express any vector as a superposition of these eigenvectors and say we're going to have 1 unit of the first bundle, 2 units of the second bundle, because it's a basis. You can equally do that, and we're going to write underline for a quantity vector, for example, expressed in this new basis. The reason that I did that is so that I can state the following proposition. When I now have a cost shock that affects all the costs, I can write this diagonalized expression for how the prices are affected. So if there is a cost shock that affects only that when I project it into this basis, is incident only on the first basis element, let's say, then it's going to only affect the prices in that same basis vector. So if I change the cost of the first bundle, it's going to change the price of the first bundle and no other prices, which is completely not true in the original way of looking at the problem, right? In the original basis, if I change my cost, it's going to change Jean-Gabriel's price and it's going to be this complicated thing. But here the system is diagonal, where each cost affects only that price. And the coefficient there is called the price pass-through, and it can be very simply written in terms of the corresponding eigenvalue of that eigenvector, right? So there's a very simple, once we diagonalize the system, rather than looking like this n by n matrix of pass-throughs for every pair, it can be summarized just by these n numbers. How much does each cost impulse in this eigenbasis translate into the price of the corresponding bundle of goods? And we can do that not only for prices, but for welfare. So given the talk length, I don't have time to elaborate on this, but there's a very canonical measure of economic welfare in the system. And just like I was able to write the price pass through in a simple way, I can write the change in welfare when I do my cost shock in a very, very succinct way, where I just sum across these n distinct eigenvectors. For each one, I have a welfare pass-through called mu, and then I multiply that by the cost shock itself and by the quantity of that bundle being consumed, and I get a very simple, I get an expression. This expression really tells me which things are important for welfare, like how much am I going to hurt or help the consumer. There's a minus sign out here because when costs go up, the consumer gets sad, right? The consumer doesn't like it when things get more expensive, but by using this decomposition, I can basically say that a good with a high welfare pass-through, or rather a bundle with a high welfare pass-through, is going to be one that really hurts the consumer when its cost goes up. So all goods are not created equal. And the idea of this is that the intensity, the kind of loading, which bundles are important, is given by this eigenvector decomposition. So let me give you maybe one thing. I'll come back to this slide, but I want to show you a picture. Have you? I can see the room pretty well. So show of hands. Who's seen a picture somewhat like this in their lives, like like a Fourier? Raise your hand if you have ever looked at something like this. Okay, so some take up, like in a firm, in a world where each node here is a firm, and they are producing complementary goods to the ones next to them. That's just a particular, toy structure you can think about. You can write down the eigenvectors, and the notation here, the visual convention, is that a green circle is a positive number, a red circle is a negative number, and the size of the circle tells me the size of the entry. So for each firm here, I have the I'm showing you the eigenvectors, and I'm depicting them by saying, positive numbers are red, negative numbers are green. Sorry, vice versa. Negative numbers are red, positive numbers are green. Sizes is magnitudes. And so there's one eigenvector, which is just the vector of all ones. There's another eigenvector, which is +1, -1, +1, -1. And in between, you have these kind of sine waves, if you'd like, that undulate around the circle. And those are the eigenvectors. So this is kind of telling you that rather than thinking of the cost shocks as they come in the original standard basis, if you transform them and think about expressing any cost shock as a superposition of these kinds of fundamental shocks, I've only shown you part of the basis here, but that's going to be sort of a useful way to look at them. In particular, we're going to be able to rank them and say this kind of shock has the biggest pass-through, and this kind of shock has the smallest pass-through. Those kinds of statements, which are completely actually, I reversed them. It turns out that this one will be the most intense and this one will be the most attenuated. And that's a much more legible way of looking at the physics of the system than you would have from the standard just write the matrix approach of economics. So now I'm going to tell you a little more sequentially, in a slightly more organized way, what it is that we do with this basic decomposition. So first we say, look, this affords a new way of looking at the mechanics of equilibrium. If you have a random driving process, which is varying your cost shocks, like you're a hedge fund analyst and you have a statistical model of how costs of firms are being driven by the war in Ukraine, then that will allow you, in combination with the right-hand column of this slide, to write down how volatile you expect prices and quantities and welfare to be. And it turns out you can write upper and lower bounds on volatility translation. That is, how much can cost volatility feed into price volatility. You can bound this stuff by the eigenvalues of your D matrix. So the spectrum of the D matrix turns out, in a sense, to be the right summary of the possible amplification that the system can afford. Now, you might say, if you're a physicist, is like, yeah, I also knew that in 1900. That's very true. Like, this is just taking the basic idea that you can use the eigenvector approach to think about the modes of your system and which ones oscillate particularly severely, but by bringing it to the particular matrix that arises from the economics of this system, you can milk those insights for their economic implications in the setting. A little more substantially, I mean, more than just the physics of it, you can also use it in optimization. So you can imagine, hey, I'm a tax authority, and I get to come in and subsidize some production. So basically, I might think, look, there's only one monopoly firm producing electric cars. And while in the long run, I don't like that, I might like to subsidize their electric cars because inefficiently many are being produced. And I have to raise that money by taxing some other goods. So how would you design that taxation exercise? It turns out that, so you could try to solve that problem without doing this change of basis. But it turns out that when you do the change of basis, you get a fantastically legible answer. You get a very simple answer that basically says something like, tax the goods that tax the eigenbundles that have high eigenvalues and subsidize the ones that have low eigenvalues. And that kind of summary answer is only available by transforming the basis in which you look at the system. And finally, and what I'll end on, because it's something that I'm most excited about, is that if your demand matrix is actually not measured reliably, if you don't actually observe demand perfectly, or you don't observe the structure of the demand spillovers, with high precision, but you have to estimate them by doing statistics. Like say you're an Amazon statistician and you get to do some price experiments and you will learn something about the spillovers in your system, but you don't know exactly how much Jean-Gabriel's demand changes when my price goes down. What can you learn? And it turns out, and this is, let me just I'll jump to this part in a second, but as you probably know, in the theory of big matrices, that's very interesting to statisticians nowadays because of big data, they have developed very rich understanding of how much you can recover about the eigenvalues and eigenvectors of a matrix when you observe a noisy version of it. And so I'll just tell you that the first basic thing we do is characterize exactly how you should do taxes and subsidies in the system, knowing D exactly, but then you don't know D exactly. And so a model is basically, rather than observing the D spillovers exactly for all goods, you observe them noisily, maybe for some goods, right? And then you have a statistical model of what the real D looks like. The question is, how close can you get to the optimal taxation outcome? So actually, you can do this for any sort of question. You might ask just, how well can I estimate the volatility response of the system? Or you can ask, how well can I design an optimal tax? I figured out how to design an optimal tax knowing D. Now, how well can I do not knowing D? And how close can I get to the Pigouvian leverage is like the bang for the buck you can get out of taxing optimally? How close can I get to that? It turns out that if you can identify and subsidize high welfare pass-through eigenvectors, you are doing okay. You can then basically collect revenue in a less systematic way and still achieve a lot of the benefits of optimal taxation. And so what I'm really excited about is that by transforming this oligopoly problem, this conventional economic problem, into this eigenvector way of looking at it, we're able to leverage results from statistics on recovering certain eigenvectors, not all eigenvectors, from very noisy data, and apply that to actually design better taxation schemes in this case, which you couldn't have done without the technology of the basis change. That's just not statistics exists only in that basis. The statistical guarantees are done in this principal components way of looking at it. So I think this is a pretty rich interaction between, on the one hand, like the statistics of these big matrices, and on the other hand, the economics of this oligopoly. I've tried to give you like a very bird's eye sketch of how the two, how we can use the statistics for economic purposes. And so what I'll do now is I'll stop here. Obviously there's stuff I've left off, which I'm very happy to dig into in the Q&A, but I just want to thank you for your attention and the excellent questions so far. And I'll turn it back over to Jean-Gabriel.